Section: Introduction. In this section, we discuss the impressive capabilities of large language models, LLMs, in various tasks like mathematical reasoning, question answering, and code generation. However, we recognize that the knowledge within these models is static, limited to the data they were trained on, which can lead to inaccuracies and outdated information. To enhance their reliability, we see the need for LLMs to access external information sources. One common solution is Retrieval Augmented Generation, RAG, which integrates external knowledge into the generation process. Early efforts in this area involved prompt-based methods that guided LLMs in generating queries and retrieving information. While these methods were effective, they required careful prompt design and placed heavy demands on the model's reasoning skills. To improve efficiency, later research looked into supervised fine-tuning, SFT, for smaller LLMs. We also noted advancements in test time scaling techniques, like Monte Carlo tree search, MCTS, which expand the search space during inference but come with high computational costs. Recently, we have seen reinforcement learning, RL, emerge as a promising approach to enhance LLM performance by improving reasoning and decision-making. Models like OpenAI O1 and DeepSeek R1 have shown significant improvements in logical reasoning through reward-based learning, without needing explicit step-by-step guidance. Several studies have explored using RL to train models that can better search for relevant information, including examples like Search R1 and Research. Notably, Deep Researcher allows interaction with live search engines, simulating real-world search environments. However, we face challenges when integrating RL with real-world search, such as unpredictable document quality from live searches and high API costs due to the need for numerous API calls. To tackle these issues, we propose ZEROSEARCH, a reinforcement learning framework that allows LLMs to learn search strategies without relying on real search engines. Our key insight is that LLMs, having gained extensive knowledge during pre-training, can generate relevant documents based on search queries. The main difference between a real search engine and our simulation lies in the style of the returned content. With lightweight supervised fine-tuning, even smaller LLMs can mimic real search engine behavior. This approach not only eliminates API costs but also allows us to control document quality. By designing prompts that distinguish between correct and incorrect answers, we enable the simulation LLM to learn to generate relevant or noisy documents by simply adjusting a few words. We also introduce a curriculum rollout mechanism during training, where the quality of generated documents is gradually reduced to simulate more challenging retrieval scenarios. This helps the model learn basic output formats before adapting to more complex situations. Importantly, ZEROSEARCH is highly scalable. Increasing the number of GPUs significantly boosts the throughput of the simulation LLM, facilitating efficient large-scale rollout. Our empirical results indicate that even a 3 billion parameter LLM can effectively enhance the policy model's search capabilities. A 7 billion parameter retrieval module performs comparably to Google Search, while a 14 billion parameter module even surpasses it. ZEROSEARCH works well with both base and instruction-tuned models of various sizes, eliminating the need for separate supervised warm-up stages. It also integrates smoothly with popular RL algorithms like Proximal Policy Optimization, PPO, and Group Relative Policy Optimization, GRPO. In summary, we present ZEROSEARCH as a novel RL framework that boosts the search capabilities of LLMs without real search engine interaction. Through supervised fine-tuning, we transform the LLM into a retrieval module that can generate both relevant and noisy documents. Our curriculum rollout mechanism progressively enhances the model's reasoning by exposing it to increasingly difficult retrieval tasks. We conducted extensive experiments, showing that ZEROSEARCH outperforms models based on real search engines while incurring no API costs and generalizing well across various LLMs and RL algorithms. Section Summary. In this section, we introduce ZEROSEARCH, a novel reinforcement learning framework that enhances the search capabilities of large language models, LLMs, without relying on real search engines. By utilizing supervised fine-tuning to generate both relevant and noisy documents, and implementing a curriculum rollout mechanism, we demonstrate that ZEROSEARCH can outperform traditional search engine-based models while eliminating API costs and maintaining scalability across various LLM sizes. Section: Related Work. In this section, we discuss related work in retrieval augmented generation and reinforcement learning. Retrieval augmented generation, or RAG, improves generation by incorporating relevant external knowledge. Early methods relied on prompts to guide large language models, LLMs, through tasks like generating queries and retrieving information. While effective, these methods often required complex prompt designs and placed heavy demands on the model's reasoning skills. To enhance efficiency and lessen reliance on powerful LLMs, later research introduced supervised fine-tuning for smaller models. For example, Self-RAG uses a self-reflection process to refine outputs, while Retro-LLM allows the model to generate detailed evidence directly from the data. Recent techniques, like Monte Carlo tree search, expand the search space during inference, with methods like RAGstar and AIR-RAG enhancing reasoning capabilities. However, these approaches can be computationally intensive, limiting their practical use. We also explore how reinforcement learning, RL, has become a valuable approach for improving LLM reasoning. Models like OpenAI O1 and DeepSeek R1 have shown strong logical inference and reasoning abilities driven by rewards rather than explicit guidance. Some studies have focused on using RL for effective information retrieval, such as Search R1, which generates multiple search queries autonomously, and R1 Searcher, which enhances search capabilities through a two-stage RL method. Research teaches models to reason through searches without supervision on intermediate steps. However, these methods often rely on static text sources like Wikipedia and struggle with real-world complexities. To address this, deep research allows direct interaction with search engines like Google, creating training environments that mimic real-world searches. While these real-time methods perform well, they face challenges like variable document quality and high API costs, which can hinder scalability. To overcome these issues, we propose ZEROSEARCH, which uses an LLM to simulate real-time searches, reducing reliance on expensive search APIs. Through lightweight supervised fine-tuning, ZEROSEARCH enables better control over document quality and incorporates a curriculum rollout mechanism for improved training stability. We then outline our reinforcement learning framework that does not require a real search engine, using an LLM to simulate one. Our optimization goal is to maximize the expected reward based on the policy model we aim to improve, the reference model, and the reward function, while keeping the simulation LLM's parameters fixed during training. In ZEROSEARCH, instead of traditional supervised fine-tuning, we implement a multi-turn interaction template that guides the policy model through reasoning and information retrieval until it reaches a final answer. This process is divided into 3 stages. First, the model expresses its reasoning, then it issues a search query if more evidence is needed, and finally, it provides an answer once enough information is gathered. This structured approach enhances the model's transparency and reliability. For search simulation tuning, we use the LLM to mimic a real search engine by generating documents in response to queries. We initially prompt the LLM to create documents, but this can lead to a noticeable difference in style compared to actual search engine outputs. To address this, we propose a lightweight supervised fine-tuning procedure. We collect interaction data by having the LLM engage with a real search engine until it finds a final answer. We label successful interactions as positive and unsuccessful ones as negative, indicating useful or noisy retrievals. We then extract query document pairs from these interactions and perform fine-tuning to enhance the LLM's ability to simulate real search engines. By adjusting prompts slightly and including the input question and answer, we broaden the LLM's knowledge. After fine-tuning, the LLM can generate both useful and noisy documents, allowing us to control document quality dynamically during rollout. Section Summary. In this section, we discuss ZEROSEARCH, a reinforcement learning framework that simulates a search engine using an LLM, eliminating the need for real search APIs. We outline our training approach, which involves a structured multi-turn interaction template for reasoning, searching, and answering, along with a lightweight supervised fine-tuning process to enhance the LLM's ability to generate relevant documents. Section: Rollout with Curriculum Search Simulation. In this section, we describe our approach to rollout with a curriculum search simulation. During the rollout, our policy model engages in interactive reasoning and creates search queries, which we then input into the simulation language model to generate relevant documents. To make training progressively more challenging, we implement a curriculum learning strategy where the quality of the generated documents decreases over time. This is managed by a probability function that determines the likelihood of producing noisy documents at each training step. As we advance in training, the chance of generating noisy documents increases, allowing the policy model to first grasp basic output structures and task requirements before tackling more complex and noisy retrieval situations. For reward design, we use a rule-based reward function that emphasizes answer accuracy. In our initial experiments, we found that relying on exact matches often led to the model generating overly lengthy answers to increase the chances of including the correct response. To address this, we switched to an F1 score-based reward, which balances precision and recall. This score is calculated based on the number of overlapping words between our predictions and the correct answers. We do not add a separate reward for output format since the model consistently produces well-structured responses without needing explicit guidance. Regarding our training algorithm, our method works well with various reinforcement learning algorithms, such as proximal policy optimization, group relative policy optimization, and Reinforce++. In our approach, the rollout sequence includes both tokens generated by our policy model and those returned by the simulation language model. To prevent training instability, we introduce a loss masking mechanism for the retrieved tokens, ensuring that we only compute gradients for our model's outputs. This helps stabilize the reinforcement learning training process while maintaining the effectiveness of retrieval augmented generation. We evaluate our method, ZEROSEARCH, on a variety of question-answering benchmarks, including single-hop and multi-hop question-answering datasets. We use exact match as our evaluation metric, considering a prediction correct if it exactly matches any normalized ground truth answer. To assess the effectiveness of ZEROSEARCH, we compare it against several baselines, including basic prompting methods, advanced retrieval augmented generation methods, and reinforcement learning tuning methods. We ensure a fair comparison by using the F1 score as the reward metric across all reinforcement learning methods, focusing on a specific baseline that avoids complex reward designs. In our experimental setup, we utilize 3 model families and simulate real-world retrieval scenarios using Google Web Search. We fix the number of retrieved documents at 5 for consistency. We merge training sets from different datasets to create a unified dataset for fine-tuning. For prompt-based baselines, we use instruct models, while for reinforcement learning methods, we evaluate both base and instruct variants. We train the simulation language model with a lightweight supervised fine-tuning approach and apply 2 reinforcement learning algorithms, GRPO and PPO, with specific learning rates and sampling strategies. Throughout our experiments, we default to using GRPO and a specific model variant for consistency. Section Summary. In this section, we describe our rollout process using a curriculum learning approach that gradually increases the difficulty of training by introducing noise in document generation, while employing a reward mechanism based on the F1 score to enhance answer accuracy. We also outline our experimental setup, including the evaluation of our method against various baselines across multiple question-answering benchmarks, utilizing reinforcement learning algorithms like GRPO and PPO for training. Section: Performance. In this section, we present the performance results of ZEROSEARCH compared to several baseline methods across 7 datasets. Our findings indicate that ZEROSEARCH consistently outperforms all baseline methods, demonstrating its effectiveness on both in-domain datasets, like NQ and Hotpot QA, and out-of-domain datasets, such as Trivia QA and others. This shows the robustness of our approach. Notably, ZEROSEARCH performs better than methods that depend on real search engines, like Search R1, highlighting its potential as a strong alternative in large-scale reinforcement learning. We also compare the reward curves of ZEROSEARCH and Search R1 using the LLMA 3.2 to 3B model. We observe that both methods show similar reward trends, with scores increasing as training progresses. However, ZEROSEARCH has a more stable learning curve, initially lagging behind but eventually surpassing Search R1 with less fluctuation, thanks to its curriculum mechanism that aids in mastering search tool usage. This generalizability is evident across both base and instruction-tuned models. Next, we explore how different simulation engine configurations impact performance, focusing on prompt-based and fine-tuned LLMs ranging from 3B to 14B parameters. Our results show that the fine-tuned 7B simulation engine performs comparably to Google Search, while the 14B version exceeds it, indicating that a well-trained LLM can effectively replace real search engines in reinforcement learning. Additionally, fine-tuned engines significantly outperform prompt-based ones, which struggle due to a distribution gap. We also find that larger models consistently improve performance, enhancing their ability to distinguish relevant documents and facilitating better curriculum learning. We then analyze the training dynamics of ZEROSEARCH by examining reward progression and interaction turns using the Llama 3.2-3B base model. Early in training, interaction turns decrease sharply while rewards increase slowly, as the policy model learns to use the search engine effectively. As training continues, both interaction turns and rewards rise sharply before stabilizing, reflecting the model's ability to retrieve relevant documents and achieve correct answers. Although rewards stabilize later, task difficulty increases, requiring the policy to refine its strategy continuously. Finally, we evaluate the performance of 2 popular RL algorithms, PPO and GRPO, within the ZEROSEARCH framework using the Qwen 2.5-3B base and LLMA 3.2 to 3B base models. Our comparison shows that both algorithms effectively enhance search capabilities, but GRPO demonstrates more stable performance across models, highlighting its training stability. We also note that GRPO's repeated rollout mechanism incurs higher API costs when interacting with real search engines, further emphasizing the advantages of our simulated search setting. Section Summary. In this section, we demonstrate that ZEROSEARCH consistently outperforms baseline methods across various datasets, showcasing its robustness and generalizability, particularly as it scales with larger models. We also find that fine-tuned simulation engines significantly surpass prompt-based methods, and our analysis of training dynamics reveals that while interaction turns decrease initially, the model quickly learns to optimize its search strategy, leading to improved rewards. Section: Reverse Curriculum Study. In this section, we analyze how effective our curriculum rollout strategy is by comparing it to a reverse curriculum approach, where the training difficulty decreases over time as we improve the quality of the documents retrieved. The results, shown in the table, clearly demonstrate that the traditional easy-to-hard curriculum consistently performs better than the reverse hard-to-easy method in both models. This supports the idea that curriculum learning is effective in our framework. By starting with better search results, we enable the policy model to learn how to use the search engine and understand the basic output format first. As we continue training, the model faces more challenging scenarios, which helps develop its reasoning skills.